Hello guys, this is 4.3 global maxima and minima. So remember earlier when we were talking about local maxima and minimum, we spoke of the idea where the if the line keeps increasing, then there is really no maximum we can talk about, right? So now instead of looking at the whole real line, we are going to just look at a segment of the x value, right? So in this case, figure 4.32, we're looking at from A to B, right? So the function f that we're going to look at is just in between a and b now. So here we will have our maximum right here in this case, right? So we can compare the the highest value of the function in this case. Okay. So here's the definition for any function f. F has a global maximum at p if f of p is less than or equal to all the values of f, and it's a global maximum if f of p is greater than or equal to all the values of f. Right. So in this case, figure 4.32, since we are cutting off the graph at a and b, we can now compare what's the highest point, what's the maximum point of the graph, right? So in this case, we can see that this point is actually the highest, has the highest function value of all the graph. So this would be your global max, right? But in the cases of 4.33, where we are looking at the entire real line, there's really no way we can determine what the global max is, because the line just goes up and never stops, right? So if we can stop the graph at some point, then we can definitely find a global max or a global minimum, right? You can see that here is the global minimum because it's the lowest point of the graph. All right, and let's learn how to do that. All right, so to find a global max and min, first we just need to compare values of the function at all critical points in the interval and the endpoint, right? So we know that the critical point will give us a local max or min, right? And we just need to add additional 2 points to compare with local max and min, right? And whichever has the greatest function value out of all these points will be the global max, and whichever has the minimum value will be the global min. All right, now to find global max and min of a continuous function on an interval excluding endpoints or on the real line, we need to find the values of the function at all critical points and sketch a graph. Okay, so let's do an example together. All right, so we are asked to find the global min and max for this function x cubed minus 6x squared minus 15x plus 100. And notice that we have a constraint on the x value. We are only looking at x values between -3 and 6. All right, so first, let's find the critical point, right, to determine whether we have a local max or min. Right, so f prime will be 3x squared minus 12x minus 15. All right, so set that equal to 0. Critical point. F prime equal to 0. So 3x squared minus 12x minus 15 is equal to 0. A little factor of 3. X minus 5. And then I have 3. X minus 5 and x plus 1 equal to 0. Okay. So the critical points that we have is x equal to 5 and -1, right? And furthermore, we can actually rewrite f prime as 3 times x minus 5 times x plus 1, which will help us determine whether these are local max or min. All right, let's do that. So I have -1 and 5. So they are 0 for f primes. 0, 0. And let's check for, let's say here, -2. f of -2, f prime of -2. That'll be 3 times -7 times -1, which will be positive. All right, and then let's do 0 in the middle. F prime of 0 will be 3 times -5 times 1, which will be negative. All right, and last, let's check um, 6. Right, so f prime of 6 will be 3 times 1 times 7, which will be positive. Okay, so by the first derivative test, right, we have critical points at -1 and 5. So at -1, it went from positive to negative, right? So positive means increasing and then decreasing, right? So here we have a local max, right? And at x equal to 5, we are decreasing to 5 and then increasing after 5. So that will be a local min. Okay. So that we have a local max and local min. Let's go ahead and find their values. So x, f of x. Let's do the critical points first. So -1 and 5. So let's see. F of -1 will be -1 to the third power minus 6 times -1 squared minus 15 times -1 plus 100. All right. So what is that? -1 minus 6 plus 15 plus 100. All right. That's 16 minus -7. That's 8, 108. 108. Okay. And 5, f of 5, which will be 5 to the third power minus 6 times 5 squared minus 15 times 5 plus 100. That will be 125 minus 150 minus 75 plus 100. All right, what is that? Negative 225, so 0. All right, so this is our local max. And that is our local min. Okay. Now, in order to find the global max and min, we have to include the function value at the endpoint, which is right here, right? We have to find the function value at x equal to -3 and 6 because these are the endpoints. Okay. So let's include the endpoints, -3 and 6. Okay. So just making a note. These two, -1 and 5, they are the critical values, critical point. And the -3 and 6, they are the endpoint. Okay, so let's go ahead and find the values at the endpoints. Okay, so for the endpoint, f of -3 is equal to -3 cubed minus 6, -3 squared minus 15 times -3 plus 100. What is that? -27, 9 minus 54 plus 45 plus 100. Okay, let's see what we have. That's 71, -71. That'll be -26, so 74. -3, 74 right here. Okay, and f of 6 is 6 cubed minus 6 times 6 squared minus 15 times 6 plus 100. All right. Let's see, 6 cubed. All right, so these two terms, they are both 6 cubed, right? So they will cancel each other out. 6 times negative 15, that's negative 80. No, not 80. Yeah, 80. Okay. No, 90 plus 100 is equal to 10. Okay, so 10. All right, so for the endpoints, the y values are 74 and 10. And the critical point, we have 108 and 0. Okay, so all we need to do is figure out, take the highest value, highest function value, which is this one right here, negative 1 and 108. So we can say negative 1 and 108, that is also a global max. And take the smallest function value, which is 0 right here, 5 and 0. That's your that's also a global min. All right, so let's attempt to graph what we have here. Okay. So we have global max at negative 1 and 108. Global min at 5, 0. And endpoints at negative 3, 74, 6, and 10. All right, so endpoints. Negative 3, 74, 6, and 10. All right, so let's attempt to graph what we have here. All right, so we're going just graphing from negative 3 to positive 6. 1, 2, 3, 4, 5, 6. Hey, so let's see. 5, 0. Right here. Easier to graph. Negative 1 and 108, which is somewhere up here. I don't know. I just call that 108. Okay. And negative 374, which will be about here. 6 and 10, let's say about here. Okay. And we know that at negative 1 and 108, that is also a local max, and 5, 0, that's a local min, right? So that means at the local max, we will have some cap like this, right? And local min will have something like this. All right, so let's just attempt to connect them together, making a better graph. Let's say like that. Okay, almost hitting it. All right, and then down like that. Oh, and then up. Yeah, it's really bad. Let me redo it. And then up. Oh my goodness. Okay, like that, and then up. Okay, so something like this, right? And this is our cutoff line, right? We cut off the graph at negative 3 and 6, right? So our local min happens to be our local max, and our our local min happens to be our global min as well. And our local max happens to be our global max as well. Okay. Okay. So to find global mix and maximum and minimum, you also always have to check the function value with the endpoint to make sure that what if your local min and local max are your global minimum and global maximum. Okay, so it's just 2 more points to check, right? The endpoint, you want to check the extra endpoint to compare if you have global max or min. All right, and that's it for 4.3, and I'll see you guys next time.